What ignites the cosmos to paint its breathtaking tapestries? Imagine a canvas vast enough to hold 1 trillion suns, each born from chaos, sculpted by gravity, and destined to fade in a blaze of glory. The universe, a relentless artist, crafts stars from swirling clouds of gas and dust, each a testament to creation's raw power. The Butterfly Nebula, known as NGC 6302, emerges as a radiant emblem of this cosmic dance. Its delicate, glowing wings, stretching across light years, belie the violent death of a star that birthed it. This celestial marvel, located 3,800 light-years away in the constellation Scorpius, captivates us with its intricate beauty, a fleeting snapshot of a star's final act. But what deeper truths lie within these stellar remnants? Could the ashes of a dying star spark the genesis of new worlds? Stars begin in nebulae, vast stellar nurseries where hydrogen and helium coalesce under gravity's unyielding pull. Picture the Orion Nebula, a glowing cradle 1,344 light-years from Earth, where dense knots of gas collapse, heating to millions of degrees. Fusion ignites and a star is born, its light piercing the cosmic void. This process, spanning millions of years, is no mere mechanics, it's a symphony of creation. Each star, from humble dwarfs to blazing giants, follows a unique path. Low-mass stars like our Sun burn steadily for billions of years, their cores fusing hydrogen into helium. Massive stars, however, live fast and die young, their intense fusion forging heavier elements like carbon, oxygen, and iron. These titans, often 20 times our Sun's mass, exhaust their fuel in mere millions of years, collapsing under their own weight in cataclysmic supernovae. The Butterfly Nebula exemplifies this dramatic end. Once a massive star, it shed its outer layers in a stellar wind, expelling gas and dust at speeds up to 600,000 miles per hour. Ultraviolet radiation from the dying star's core excites the surrounding material, creating a glowing masterpiece. Its wings, sculpted by intense stellar winds, span over 2 light-years, with temperatures reaching 20,000 Kelvin. This isn't mere destruction, it's transformation. The nebula's dust, rich in carbon and silicates, scatters into space, joining the interstellar medium. These particles, forged in the hearts of ancient stars, become the seeds of new celestial bodies. Planets, moons, and even the building blocks of life owe their existence to this cosmic recycling. Consider the profound cycle at play. A star's death is not an end, but a gift to the universe. The elements in your body, carbon in your cells, oxygen in your breath were once forged in stellar crucibles. We are, quite literally, star stuff. The Butterfly Nebula, with its ethereal glow, reminds us of this connection, bridging the cosmic and the personal. Its beauty lies not just in its form, but in its story. A star's sacrifice fuels creation anew. Yet this raises a tantalizing question. Could these stellar remnants hold secrets beyond mere matter? Might they whisper clues to the origins of life itself, or even the potential for alien world? This cycle of birth and death mirrors the universe's broader evolution. Galaxies form from the gravitational dance of stars and gas, growing through mergers and collisions. Our Milky Way, home to 100 billion stars, was shaped by such cosmic alchemy. Each star's life cycle contributes to this grand narrative, from the first hydrogen clouds 13.8 billion years ago to the complex galaxies we see today. The Butterfly Nebula, a fleeting moment in cosmic time, embodies this eternal rhythm. Its glowing wings, a testament to destruction, also signal rebirth as its dust scatters to form new stars and planets. But the cosmos is not just a factory of stars, it's a realm of mystery. Why do some stars end in nebulae like NGC 6302, while others collapse into black holes? What determines the fate of a star's remnants? These questions pull us deeper into the universe's enigma. The Butterfly Nebula, with its intricate patterns, challenges us to look beyond the visible. Its dust grains, some no larger than a micron, could hold chemical signatures of prebiotic molecules, Scientists speculate that such particles drifting through space might seed planets with the ingredients for life. This possibility transforms the nebula from a celestial artwork into a potential cradle of existence. As we marvel at the cosmos, we confront our own place within it. The birth and death of stars played out over eons dwarf our fleeting lives. Yet, this vastness sparks curiosity, not insignificance. The Butterfly Nebula, with its radiant symmetry, invites us to ponder the universe's purpose. Is it a cosmic accident, or does it pulse with intention? Each star, each nebula tells a story of creation and destruction, a cycle that echoes in our own quest for meaning. The dust from a dying star scattered across the void might hold the key to new worlds, perhaps even ones that mirror our own. This cosmic narrative sets the stage for a deeper exploration. If stellar remnants can birth planets, could they also nurture life? The Butterfly Nebula, a beacon of transformation, hints at possibilities beyond our grasp. As we trace the journey of stardust, we edge closer to unraveling the universe's greatest mysteries. What secrets lie in the ashes of stars, and how might they reshape our understanding of existence itself? What sparks a star's fleeting existence in the infinite cosmos? Picture a universe teeming with raw potential, where vast clouds of gas and dust collapse under gravity's relentless embrace, giving birth to radiant beacons. Stars, the universe's alchemical engines, forge light and matter through cycles of creation and destruction. The Butterfly Nebula, NGC 6302, stands as a vivid testament to this cosmic saga, a dying star's luminous farewell, its glowing wings a canvas of transformation. But how does a star's journey unfold from its fiery inception to its dramatic end? And what secrets might its final act unveil about the universe's deepest mystery? Stars emerge from nebula, colossal clouds of hydrogen, helium, and trace elements. Consider the Eagle Nebula, 6,500 light-years away, where towering pillars of gas nurture embryonic stars. Gravity pulls these clouds inward, compressing them until temperatures soar to 10 million Kelvin, igniting nuclear fusion. Hydrogen fuses into helium, releasing energy that makes a star shine. This marks a star's entry onto the main sequence, where it spends most of its life. Our Sun, a modest G-type star, has burned for 4.6 billion years and will continue for another 5 billion, steadily fusing hydrogen in its core. Yet, not all stars follow this tranquil path. Massive stars, up to 100 times the Sun's mass, blaze through their fuel in mere millions of years, their cores a frenetic forge of heavier elements. A star's life hinges on its mass. Low-mass stars, like red dwarfs, burn slowly, enduring for trillions of years. Massive stars, however, race toward explosive fates. As a star exhausts its hydrogen, its core contracts, heating until helium fuses into carbon and oxygen. For massive stars, this process cascades, forging neon, magnesium, and iron. Each stage is shorter, more intense, until the core can no longer resist gravity's crush. The star's fate, its final act, depends on its mass. Smaller stars, like our Sun, shed their outer layers, forming glowing shells called planetary nebulae. These delicate structures, often mistaken for planets in early telescopes, are the remnants of stars between 0.8 and 8 solar masses. The Butterfly Nebula exemplifies this, its intricate wings sculpted by stellar winds. Massive stars, above 8 solar masses, meet a different end. Their cores collapse, triggering supernovae cataclysmic explosions that outshine entire galaxies. A star 20 times the Sun's mass might collapse into a neutron star, a dense sphere of neutrons just 12 miles across, with gravity so intense a teaspoon weighs as much as a mountain. Larger stars, above 20 solar masses, collapse further, forming black holes regions where gravity warps space-time, swallowing light itself. These fates, from glowing nebulae to enigmatic voids, highlight the universe's diversity. Yet each end is generative. Supernovae scatter heavy elements, carbon, silicon, gold into space, seeding future stars and planets. Even black holes may shape galaxies, their gravity anchoring stellar orbit. The Butterfly Nebula, 3,800 light-years distant, illustrates this dual nature of destruction and creation. Its progenitor, a star several times the Sun's mass, exhausted. Its fuel shedding its outer layers in a stellar wind traveling at 600,000 miles per hour. The remaining core, a white dwarf, emits intense ultraviolet radiation, illuminating the ejected gas. This creates the nebula's glowing wings, stretching over 2 light-years, with temperatures reaching 20,000 Kelvin. The nebula's dust, rich in silicates and carbon, drifts into the interstellar medium, becoming raw material for new celestial bodies. This process mirrors the universe's recycling system where death fuels birth. The elements in our planet, our bodies, even our breath, were forged in such stellar crucibles. But what makes a star's end so revealing? Planetary nebulae like NGC 6302 offer a window into stellar interiors. Their chemical compositions, nitrogen, oxygen, neon, reveal the fusion processes that occurred within. By studying their spectra, astronomers decode a star's history from its initial mass to its final moments. The Butterfly Nebula's intricate structure, shaped by competing stellar winds, suggests a complex interplay of forces. Some hypothesize a binary star system at its heart, where a companion star's gravity sculpted the nebula's symmetry. This complexity hints at broader cosmic processes where interactions between stars shape the universe's evolution. The life cycle of stars also raises profound questions. Why do some stars form planetary nebulae, while others collapse into black holes? The answer lies in the delicate balance of mass and gravity. A star like our Sun will end as a white dwarf, cooling over billions of years within a fading nebula. A massive star's collapse, however, can warp the fabric of reality itself. Black holes, with their event horizons, challenge our understanding of physics, hinting at connections to quantum mechanics and the universe's origins. Could the remnants of these stellar deaths hold clues to the Big Bang, when all matter was forged? This cosmic cycle, birth, life, death, echoes in the universe's broader narrative. Galaxies, like our Milky Way, form from the gravitational dance of stars and gas. Over billions of years, they merge, grow, and evolve, shaped by the same forces that govern stars. The Butterfly Nebula, a fleeting moment in this saga, embodies transformation. Its dust grains, some smaller than a micron, may carry prebiotic molecules, suggesting that stellar deaths could seed life across the cosmos. This possibility transforms our view of nebulae from mere spectacles to potential cradles of existence. As we ponder this cycle, we confront our place in the cosmos. The elements in our DNA, the iron in our blood, were born in stars long gone. The Butterfly Nebula, with its radiant wings, connects us to this ancient lineage. Its beauty lies not just in its glow, but in its story, a star's sacrifice that fuels creation. Yet this raises a deeper mystery. If stellar dust can birth planets, could it also nurture life? The nebula's remnants drifting through space might hold answers to the origins of worlds like ours. This exploration of stellar life cycles sets the stage for a grander question. If the ashes of stars can spark new worlds, what else might they reveal? The Butterfly Nebula, a beacon of cosmic renewal, invites us to probe deeper. Could its dust hold the key to understanding not just the universe's past, but its future, and perhaps the existence of life beyond Earth? What cosmic artistry could sculpt wings of light across the void? The Butterfly Nebula, NGC 6302, dazzles with its ethereal symmetry, a celestial masterpiece born from a star's dying breath. Located 3,800 light-years away in Scorpius, its glowing tendrils stretch over 2 light-years, a radiant paradox of beauty and violence. How does a star's demise create such delicate splendor? This nebula, discovered in 1826 by James Dunlop, captivates astronomers and dreamers alike. its butterfly-like form inviting us to unravel the interplay of stellar forces and cosmic alchemy. Its intricate structure, forged by a star's final throes, whispers secrets of the universe's creative power. The Butterfly Nebula's discovery marked a turning point in our understanding of stellar evolution. Early astronomers peering through rudimentary telescopes mistook such glowing clouds for planets, dubbing them planetary nebulae. Dunlop's observations, followed by detailed studies in the 20th century, revealed NGC 6302 as a stellar remnant. By the 1980s, the Hubble Space Telescope unveiled its stunning detail: two luminous lobes resembling butterfly wings, bisected by a dark lane of dust. This structure, glowing in hues of red, green and blue, results from ionized gases like oxygen and nitrogen, excited by the intense radiation of the nebula's central star. The nebula's vivid colors and sharp edges, captured in high-resolution images, evoke awe, blending scientific precision with poetic wonder. At its heart lies a white dwarf, the collapsed core of a star once several times our sun's mass. This remnant, scorching at 250,000 Kelvin, emits fierce ultraviolet radiation, illuminating the surrounding gas. The star's rapid rotation, possibly accelerated by a companion star, shaped the nebula's distinctive form. As the star neared its end, it shed its outer layers in powerful stellar winds, ejecting gas at speeds up to 600,000 miles per hour. These winds, colliding with earlier ejections, sculpted the nebula's bipolar structure, two lobes extending outward, like wings caught in cosmic flight. The dark equatorial band, dense with dust, absorbs light, enhancing the contrast of the glowing lobes. This interplay of forces creates a visual symphony, a delicate balance of chaos and order. The nebula's composition offers clues to its origins. Spectroscopic analysis reveals a rich mix of elements: hydrogen, helium, oxygen, nitrogen, and carbon, forged in the star's core during its lifetime. The dust grains, some smaller than a micron, contain silicates and carbon compounds, potential precursors to planetary systems. These particles, scattered into the interstellar medium, may seed new stars and planets, linking the nebula's beauty to the universe's creative cycle. The presence of complex molecules, detected through infrared observations, hints at chemical processes that could foster prebiotic materials. This transforms NGC 6302 from a mere spectacle into a cosmic laboratory, where the building blocks of worlds take shape. The Butterfly Nebula's structure is a puzzle of astrophysical dynamics. Its bipolar lobes suggest a rapid, asymmetric expulsion of material, possibly driven by a binary star system. One theory posits that a companion star's gravitational influence funneled the outflowing gas into two streams, creating the wing-like form. Alternatively, the central star's fast rotation may have ejected material preferentially along its equator, shaping the nebula's hourglass figure. Magnetic fields generated within the star could also play a role, channeling gas into structured jets. These competing forces, gravity, rotation, magnetism, interweave to craft a form that appears almost intentional, as if the universe sculpted a monument to its own ingenuity. Yet the nebula's beauty masks its violent origin. The star's death throes unleashed energies rivaling supernovae, with temperatures in the lobes reaching 20,000 Kelvin. The intense radiation strips electrons from atoms, creating the nebula's glow. This process, known as ionization, paints the nebula in vibrant colors: blue from helium, green from oxygen, red from nitrogen. The lobe's sharp edges, sculpted by high-speed winds, contrast with the diffuse glow of earlier ejections, creating a layered complexity. The central star, now a white dwarf, is obscured by the dense dust lane, adding mystery to its role as the nebula's architect. This tension between creation and destruction defines NGC 6302's allure. The nebula's fleeting nature adds to its poignancy. Planetary nebulae last only 10,000 to 20,000 years before dispersing, a mere blink in cosmic time. The Butterfly Nebula, already thousands of years old, is fading, its gases thinning into the interstellar void. Yet, its legacy endures. The dust and gas it releases will merge with nearby clouds, potentially triggering new star formation. This cycle of renewal, where a star's death fuels future creation, mirrors the universe's relentless evolution. The nebula's delicate wings glowing against the dark symbolize this paradox, an end that births beginnings. For our audience, the Butterfly Nebula is more than a scientific curiosity, it's a philosophical touchstone. Its beauty invites reflection on our place in the cosmos. The elements in its dust, forged in a star's heart, connect us to the universe's ancient past. Carbon in our cells, oxygen in our lungs. These are gifts from stars like NGC 6302's progenitor. This connection sparks wonder. If a dying star can create such splendor, what other marvels might its remnants inspire? Could its dust, drifting across light years, carry the seeds of life to distant worlds? The nebula's structure also challenges our understanding of cosmic order. Its symmetry suggests hidden forces at play, perhaps a binary dance or magnetic sculpting. These mysteries pull us deeper, urging us to question the universe's design. Is its beauty a byproduct of physics, or does it hint at a deeper purpose? The Butterfly Nebula, with its glowing wings, stands as a bridge between science and speculation, inviting us to explore both the tangible and the unknown. As we linger on NGC 6302's radiant form, we're drawn to a broader question. If a star's death can create such intricate beauty, what else might it reveal? The nebula's dust, rich with potential, could hold clues to the origins of planets, life, even civilizations. Its fleeting existence reminds us of the universe's impermanence, yet its legacy points to eternal renewal. This stellar masterpiece, born from chaos, sets the stage for a deeper inquiry. Could the remnants of stars like this one unlock the secrets of existence itself? What becomes of a star's final breath? In the vastness of space, where stars blaze and fade, their remnants, mere wisps of dust and gas, hold the power to shape new worlds. The Butterfly Nebula, with its radiant wings, scatters its stellar ashes across light years, enriching the cosmos with the seeds of creation. These particles, born from a star's fiery end, seem insignificant, yet they are the universe's raw materials, forging stars, planets, and perhaps life itself. How can destruction yield such profound beginning? This cosmic alchemy, where death fuels rebirth, challenges our view of the universe as a place of endings, revealing instead a cycle of eternal renewal. The interstellar medium, the vast space between stars, is a dynamic tapestry of gas and dust. Comprising mostly hydrogen and helium, it also contains trace amounts of heavier elements: carbon, oxygen, silicon, forged in stellar cores. When a star like the Butterfly Nebula's progenitor dies, it expels these materials in stellar winds or explosive supernovae. The nebula, 3,800 light-years away, releases gas at speeds of 600,000 miles per hour, laden with dust grains smaller than a micron. These particles, though minuscule, are potent. They absorb and scatter starlight, cooling gas clouds to trigger collapse. This process, observed in regions like the Orion Nebula, sparks the birth of new stars, as gravity pulls dust and gas into dense knots, igniting fusion. Dust, often dismissed as cosmic debris, is a cornerstone of creation. Composed of silicates, carbon compounds, and even ice, these grains form in the outer layers of dying stars. In planetary nebulae like NGC 6302, the intense radiation from a white dwarf heats these particles, causing them to glow in infrared. This glow, detected by telescopes like Spitzer, reveals a chemical richness: polycyclic aromatic hydrocarbons, potential precursors to organic molecules. These compounds, drifting through space, may settle on nascent planets, providing the building blocks for life. The carbon in our DNA, the oxygen in our air, these elements were once dust, expelled by stars long vanished. This connection binds us to the cosmos, making us children of stellar sacrifice. The gas, too, plays a vital role. Hydrogen and helium, the universe's primordial elements, dominate the interstellar medium. but dying stars enrich it with heavier elements. Supernovae from massive stars, 8 to 100 times the Sun's mass, blast nitrogen, iron, and gold into space. These explosions, brighter than 1 billion suns, scatter their bounty across galaxies. In the Milky Way, such events have shaped its 100 billion stars, each a product of recycled material. The gas, ionized by stellar radiation, glows in nebulae, creating stunning vistas like the Crab Nebula, a supernova remnant 6,500 light-years away. This gas, cooling over millennia, clumps with dust to form new stellar nurseries, perpetuating the cosmic cycle. This interplay of destruction and creation is vivid in the Butterfly Nebula. Its dying star, once several times the Sun's mass, shed its outer layers, creating a glowing shell of gas and dust. The white dwarf at its core, burning at 250,000 Kelvin, ionizes the surrounding gas, producing the nebula's vibrant colors: blue helium, green oxygen, red nitrogen. The dust, rich in silicates, scatters into the interstellar medium, joining clouds that may collapse into new stars. This process, observed across galaxies, underscores a profound truth. A star's death is not an end, but a gift. Its remnants, dispersed across light years, become the raw material for planets, moons, and potentially life. The creative potential of dust and gas extends beyond stars. Planets form in protoplanetary disks, swirling rings of material around young stars. The dust grains collide, sticking together to form pebbles, then boulders, and eventually planets. In our solar system, 4.6 billion years ago, such a disk birthed Earth, its elements drawn from ancient stellar remnants. The Butterfly Nebula's dust, with its complex molecules, hints at a similar role. Infrared spectra reveal carbon-based compounds, suggesting that such nebulae could seed planets with the ingredients for life. This possibility transforms our view of stellar death from a moment of loss to a catalyst for existence. Yet the process is not without mystery. Why do some dust grains survive the harsh radiation of a dying star? How do they coalesce into planet? Observations of young stars, like those in the Taurus molecular cloud, show dust grains growing over millions of years, but the exact mechanisms remain elusive. Magnetic fields, turbulence, and even the shape of dust grains, spherical or jagged, play a role. In the Butterfly Nebula, the dust's survival amid intense stellar winds suggests resilience, perhaps due to its chemical makeup. These grains, drifting through space, may carry prebiotic molecules, raising a tantalizing question. Could they spark life on distant worlds? The cosmic cycle of dust and gas also shapes galaxies. The Milky Way, 100,000 light-years across, owes its spiral arms to the gravitational dance of stars and gas. Supernovae and stellar winds stir the interstellar medium, triggering waves of star formation. In galaxies like Andromeda, 2.5 million light-years away, similar processes unfold, with dust and gas fueling stellar nurseries. This dynamic interplay, observed through radio telescopes, reveals a universe in constant flux, where destruction and creation are two sides of the same coin. The Butterfly Nebula, with its glowing lobes, embodies this duality, its dust a testament to the universe's regenerative power. This cycle challenges our notions of life and death. On Earth, we see endings as final, but in the cosmos, death is a prelude to creation. The elements in our bodies, forged in ancient stars, connect us to this cycle. The Butterfly Nebula's dust, scattering across the void, may one day form planets, orbiting alien suns. This thought sparks wonder. Are we alone? Or is the universe teeming with worlds born from stellar ashes? The nebula's legacy, fleeting yet eternal, invites us to ponder our place in this cosmic tapestry. The significance of dust and gas extends to the universe's origins. The Big Bang, 13.8 billion years ago, produced only hydrogen, helium, and trace lithium. Heavier elements, essential for planets and life, were forged in stars. Each supernova, each planetary nebula, enriches the cosmos, building complexity from simplicity. The Butterfly Nebula, with its intricate chemistry, hints At this evolution, its dust a bridge between the universe's past and future. Could these particles hold clues to the first stars, or even the origins of life itself? As we marvel at this cosmic recycling, we confront a deeper mystery. If dust and gas can birth planets, could they also nurture life? The Butterfly Nebula, with its radiant wings, suggests a universe where creation emerges from loss. Its dust, drifting through space, may carry the seeds of worlds unknown. This possibility sets the stage for a profound question. What role do these stellar remnants play in the search for life beyond Earth? And how might they reshape our understanding of the cosmos? What secrets do the glowing shells of dying stars hold? Planetary nebulae like the radiant Butterfly Nebula are cosmic crucibles where destruction births creation. These ethereal clouds, cast off by stars in their final throes, scatter elements essential for new stars, planets, and perhaps life itself. NGC 6302, with its luminous wings spanning light years, embodies this paradox. A star's death illuminates the path to cosmic renewal. How do these celestial laboratories transform stellar ashes into the building blocks of existence? By blending scientific rigor with philosophical wonder, we uncover a universe where endings spark beginning, challenging us to see death as the cradle of life. Planetary nebulae form when stars like our Sun, or those up to 8 times its mass, exhaust their nuclear fuel. As their cores collapse into white dwarfs, they shed outer layers in powerful stellar winds, creating glowing shells of gas and dust. The Butterfly Nebula, 3,800 light-years away in Scorpius, exemplifies this process. Its progenitor star, once several times the Sun's mass, expelled gas at speeds of 600,000 miles per hour, forming 2 radiant lobes. The white dwarf at its core, blazing at 250,000 Kelvin, bathes these gases in ultraviolet radiation, causing them to glow with vibrant colors: blue helium, green oxygen, red nitrogen. This spectacle, visible through telescopes like Hubble, reveals a chemical richness forged in the star's heart. These nebulae are more than cosmic artworks, they are laboratories of creation. The Butterfly Nebula's ejected material contains heavy elements, carbon, oxygen, nitrogen synthesized during the star's lifetime. As hydrogen fused into helium, then helium into carbon and oxygen, the star became a forge of cosmic ingredients. When it shed its outer layers, these elements scattered into the interstellar medium, enriching it with the raw materials for new celestial bodies. Spectroscopic studies of NGC 6302 reveal a complex chemistry: silicates, carbon compounds, and even polycyclic aromatic hydrocarbons, molecules linked to organic life. These particles, some smaller than a micron, drift through space, potentially seeding planets with the precursors of biology. The creative power of planetary nebulae lies in their role as cosmic recyclers. Unlike massive stars that explode as supernovae, stars forming planetary nebulae release their material gently, preserving complex molecules. The Butterfly Nebula's dust grains, illuminated by infrared telescopes like Spitzer, show traces of water vapor and crystalline silicates, materials found in comets and planetary disks. This suggests a direct link between stellar death and planet formation. In protoplanetary disks around young stars, such dust coalesces into pebbles, then planetesimals, and eventually planets. Earth's own elements, carbon in our cells, oxygen in our breath, trace back to such nebulae cast off by ancient stars billions of years ago. This cycle of renewal challenges our perception of destruction. A star's death, far from being an end, is a generative act. The Butterfly Nebula's glowing lobes, stretching over 2 light years, are a testament to this. Their intricate structure, shaped by competing stellar winds, hints at complex dynamics, perhaps a binary star system sculpting the gas into symmetrical wings. The nebula's dust, rich in carbon-based molecules, may carry the seeds of life. Scientists speculate that such compounds, surviving the harsh radiation of a white dwarf, could settle on nascent planets, fostering chemical reactions that lead to amino acids or other organic building blocks. This transforms planetary nebulae into cosmic laboratories where the chemistry of life takes shape. The scientific study of these nebulae reveals their complexity. Using spectroscopy, astronomers analyze the light emitted by ionized gases, decoding the nebula's composition and temperature. In NGC 6302, the presence of nitrogen and oxygen suggests a star that underwent intense fusion, while its dust grains indicate a carbon-rich environment. These observations, combined with computer models, show how stellar winds shape the nebula's form. Fast winds from the white dwarf collide with slower, earlier ejections, creating shock fronts that sculpt the glowing lobes. Magnetic fields or a companion star may further refine this structure, adding to the nebula's mystery. Each detail offers clues to the star's history and the universe's evolution. Yet planetary nebulae also inspire philosophical reflection. Their fleeting existence, lasting only 10,000 to 20,000 years, mirrors the impermanence of life. The Butterfly Nebula, already thousands of years old, will soon fade, its gases dispersing into the cosmos. But its legacy endures. The dust it releases joins molecular clouds, triggering new star formation in regions like the Taurus molecular cloud, 450 light-years away. This cycle, observed across galaxies, suggests a universe in constant renewal, where death fuels creation. The elements in our bodies, forged in such nebulae, connect us to this cosmic rhythm, making us part of an eternal story. This interplay of science and philosophy captivates our imagination. If planetary nebulae can produce the elements of life, could they also seed alien worlds? The Butterfly Nebula's chemical complexity hints at this possibility. Its carbon-rich dust, drifting through space, may settle in distant systems, sparking the chemistry of life. This raises a profound question. Are we alone, or is the universe teeming with worlds born from stellar ashes? The nebula's radiant wings glowing against the void invite us to ponder the origins of existence itself, blending awe with speculation. The broader cosmic context amplifies this significance. Galaxies like our Milky Way, home to 100 billion stars, rely on planetary nebulae and supernovae to enrich their interstellar medium. Over 13.8 billion years, these processes have built the complexity we see today, from simple hydrogen clouds to intricate galaxies. The Butterfly Nebula, though a single moment in this saga, contributes to this evolution. Its dust, merging with nearby clouds, may trigger new stellar nurseries, perpetuating the cycle. This dynamic interplay, observed through radio and X-ray telescopes, reveals a universe alive with possibility. The contrast between destruction and creation defines planetary nebulae. Their glowing shells, born from a star's collapse, are not mere remnants, but engines of cosmic renewal. The Butterfly Nebula's delicate beauty belies its violent origins, where stellar winds and radiation sculpt chaos into order. This paradox resonates with our audience, who seek both scientific insight and existential meaning. The nebula's elements, scattered across light years, connect us to the cosmos, reminding us that we are star stuff forged in the hearts of dying stars. As we explore these cosmic laboratories, we confront a deeper mystery. If planetary nebulae can produce the building blocks of life, what else might they reveal? The Butterfly Nebula, with its radiant symmetry, suggests a universe where death is not an end, but a catalyst. Its dust, rich with potential, may hold clues to the origins of life across the cosmos. This possibility pulls us toward a grander question. Could these stellar remnants unlock the secrets of alien worlds, reshaping our understanding of life's place in the universe? Could the ashes of a dying star ignite the spark of life? In the vast, frigid void of space, where temperatures plummet to near absolute zero, the Butterfly Nebula's dust glimmers with possibility. These microscopic grains, cast off by a star's final throes, carry carbon, oxygen, and nitrogen elements woven into the fabric of life. Far from Earth, 3,800 light-years away, NGC 6302's radiant wings hint at a cosmic chemistry that transforms sterile space into a crucible for creation. How do these stellar remnants, born in chaos, foster the complex molecules that might seed Life across the universe? This question bridges the sterile cosmos with the vibrant potential of existence. Stellar dust, though seemingly insignificant, is a chemical powerhouse. When a star like the Butterfly Nebula's progenitor dies, it expels its outer layers, releasing dust grains rich in silicates, carbon, and organic compound. These particles, some smaller than a micron, form in the cooling envelopes of dying stars where temperatures drop enough for atoms to bond into molecules. Infrared observations of NGC 6302 reveal polycyclic aromatic hydrocarbons, PAHs, complex carbon-based molecules resembling the building blocks of life. These compounds, stable even in the harsh radiation of a white dwarf, drift into the interstellar medium, joining molecular clouds where new stars and planets form. The chemistry of these dust grains is astonishingly complex. In the Butterfly Nebula, the white dwarf's intense ultraviolet radiation at 250,000 Kelvin excites surrounding gases, triggering chemical reactions. Hydrogen combines with carbon to form hydrocarbons. Oxygen bonds with silicon to create silicates. Some grains harbor water ice or carbon dioxide, detected through spectroscopy by telescopes like Spitzer. These molecules, forged in the star's death, are not mere debris but precursors to life. On Earth, similar compounds, amino acids, nuclear bases, form the foundation of biology. The presence of PAHs in nebulae suggests that the cosmos is a vast laboratory where the seeds of life are sown across light years. This chemistry unfolds in the interstellar medium, a sparse yet dynamic realm. Molecular clouds like the Taurus. Molecular cloud 450 light-years away are dense regions where dust and gas coalesce. Shielded from stellar radiation, these clouds allow complex molecules to form. Dust grains act as catalysts, their surfaces providing sites for atoms to collide and bond. For example, hydrogen molecules form when atoms stick to a grain surface, combining before drifting off. In the Butterfly Nebula, such processes produce organic molecules that survive the nebula's intense environment, scattering into space to join these clouds. Over millions of years, these grains may become part of protoplanetary disks where planets take shape. The contrast between space's sterility and its creative potential is striking. Space is a near-perfect vacuum with densities a trillion times lower than Earth's atmosphere. Yet within this emptiness, chemistry thrives. Dust grains, coated with ice in cold molecular clouds, foster reactions that produce methanol, formaldehyde, and even glycine, an amino acid found in proteins. Laboratory experiments simulating interstellar conditions show that ultraviolet light and cosmic rays can drive these reactions, transforming simple atoms into complex organics. The Butterfly Nebula's dust, rich in carbon compounds, suggests that such processes are universal, occurring in nebulae across galaxies like our Milky Way, home to 100 billion stars. This cosmic chemistry connects directly to planet formation. In protoplanetary disks, dust grains collide and stick, growing from microns to kilometers over millions of years. The Butterfly Nebula's dust, carrying PAHs and silicates, could settle into such disks, delivering the elements needed for rocky planets like Earth. Our planet's carbon, essential for life, likely originated in similar nebulae delivered by comets or asteroids formed from stellar dust. The discovery of amino acids in meteorites, like the Murchison meteorite, supports this idea, showing that organic molecules from space can survive planetary formation. This suggests that the Butterfly Nebula's remnants could seed distant worlds with the ingredients for life. But how do these molecules transition from cosmic dust to living systems? The process remains a mystery. On Earth, life emerged in a warm, wet environment where organic molecules interacted in primordial oceans. In space, conditions are harsher, yet chemistry persists. In the Butterfly Nebula, high-energy radiation drives the formation of complex molecules, some resembling the sugars and amino acids found in DNA. These molecules, protected within dust grains, can survive journeys across light years, landing on planets with liquid water. Exoplanet studies, such as those of TRAPPIST-1's rocky worlds, suggest that such planets are common, raising the possibility that stellar dust seeds life far beyond our solar system. This possibility captivates our imagination. If the Butterfly Nebula's dust can produce organic molecules, could it spark life elsewhere? The nebula's chemical richness, revealed through infrared and radio observations, hints at a universe teeming with potential. PAH is found in NGC 6302 are also detected in distant galaxies, suggesting that the chemistry of life is universal. This challenges our view of space as barren, recasting it as a fertile ground for creation. The nebula's dust, drifting through the cosmos, may carry the seeds of life to planets orbiting alien suns, linking our existence to a broader cosmic narrative. Philosophically, this cycle of creation resonates deeply. The Butterfly Nebula's radiant wings, born from a star's demise, symbolize a universe where death enables life. The carbon in our bodies, the oxygen we breathe, these are gifts from ancient stars, their dust woven into our being. This connection sparks awe. We are not separate from the cosmos, but part of its story. The nebula's fleeting beauty, lasting only 10,000 to 20,000 years, mirrors life's impermanence, yet its legacy endures in the molecules it scatters. This duality, destruction and creation, invites us to ponder our place in an ever-evolving universe. The scientific exploration of stellar dust also raises profound questions. How do simple atoms form complex molecules in space's harsh environment? Laboratory simulations suggest that cosmic rays and ultraviolet light drive these reactions, but the exact pathways remain elusive. In the Butterfly Nebula, the presence of water vapor and organic compounds hints at chemical resilience, perhaps due to the protective role of dust grains. These grains, acting as tiny shields, preserve molecules that might otherwise be destroyed. This resilience suggests that the chemistry of life is not unique to Earth, but a cosmic phenomenon, occurring wherever stars die. The broader context of galactic evolution amplifies this idea. The Milky Way, shaped by 13.8 billion years of stellar births and deaths, relies on nebulae like NGC 6302 to enrich its interstellar medium. Each planetary nebula, each supernova, adds to this chemical complexity, building the elements needed for planets and life. The Butterfly Nebula's dust, merging with molecular clouds, may trigger new star formation, perpetuating the cycle. This dynamic process, observed through telescopes like ALMA, reveals a universe in constant transformation, where every end fuels a new beginning. As we reflect on this cosmic chemistry, we confront a tantalizing possibility. If stellar dust can produce the building blocks of life, could it also spark life on other worlds? The Butterfly Nebula, with its glowing lobes, stands as a beacon of this potential. Its dust, rich with organic molecules, may hold the key to understanding life's origins across the cosmos. This possibility pulls us toward a deeper question. Are we alone, or is the universe alive with worlds born from the same stellar ashes that created us? What cosmic forces forge the elements of existence? The universe, a vast crucible, transforms simple atoms into the building blocks of stars, planets, and life through the cataclysmic deaths of stars. Supernovae, the explosive finales of massive stars, hurl heavy elements like iron and gold into the void, while gentler stellar winds from stars like the Butterfly Nebula's progenitor scatter lighter elements such as carbon and oxygen. These processes, though vastly different in their violence, enrich the cosmos, seeding it with the raw materials for creation. How do these stellar deaths, one ferocious and the other serene, weave the intricate tapestry of the universe's chemistry, linking destruction to the promise of life? Stars are the universe's alchemists, forging elements through nuclear fusion. In their cores, hydrogen fuses into helium, releasing energy that powers their radiance. For stars like our Sun, this process continues for billions of years, producing lighter elements. But massive stars, those exceeding 8 solar masses, push further, their intense pressures and temperatures fusing helium into carbon, oxygen, and beyond neon, magnesium, silicon, and iron. The Butterfly Nebula, 3,800 light-years away in Scorpius, emerged from a star several times our Sun's mass. As it neared its end, it shed its outer layers in stellar winds, releasing carbon and oxygen into space. These winds, traveling at 600,000 miles per hour, formed the nebula's glowing wings, a delicate contrast to the explosive fury of supernovae. Supernovae, the deaths of stars above 8 solar masses, are cosmic spectacles. When a massive star exhausts its fuel, its core collapses under gravity's relentless pull, triggering an explosion that outshines entire galaxies. The Crab Nebula, 6,500 light-years away, marks such an event, observed by Chinese astronomers in 1054 CE. These blasts, reaching temperatures of 100 billion Kelvin, forge heavy elements in milliseconds. Rapid neutron capture, or the R process, produces gold, silver, uranium, and others, which are then blasted into space. A single supernova can release more energy than our Sun will emit in its 10 billion-year lifetime, scattering its elemental bounty across light-years, enriching the interstellar medium for future star formation. Stellar winds, by contrast, are a gentler force. In stars like the Butterfly Nebula's progenitor, the outer layers are shed gradually, forming planetary nebulae. These winds, driven by radiation pressure, carry lighter elements, carbon, nitrogen, oxygen, into the cosmos. The Butterfly Nebula's white dwarf, burning at 250,000 Kelvin, illuminates its ejected gas, creating a glowing shell that spans 2 light-years. Spectroscopic analysis reveals a rich chemistry, silicates, carbon compounds, and traces of water vapor. Unlike supernovae, which destroy their stars in an instant, planetary nebulae preserve complex molecules, allowing them to survive and integrate into molecular clouds where they may spark new stars or planets. The contrast between these processes highlights their complementary roles. Supernovae produce heavy elements essential for rocky planets and life. Iron in our blood, calcium in our bones, these trace back to ancient supernovae. Planetary nebulae like NGC 6302 contribute lighter elements, crucial for organic chemistry. Carbon, the backbone of life, and oxygen, vital for water, are abundant in these nebulae. Together, these processes enrich the interstellar medium, a dynamic sea of gas and dust that spans galaxies. In the Milky Way, home to 100 billion stars, this enriched medium fuels the formation of new stellar systems, perpetuating a cycle of cosmic renewal. The chemistry of this cycle is profound. Supernovae scatter heavy elements through shock waves, stirring molecular clouds like the Orion Nebula, 1,344 light-years away, where new stars are born. The dust and gas from these explosions, combined with contributions from planetary nebulae, create a diverse chemical reservoir. Infrared observations of the Butterfly Nebula reveal polycyclic aromatic hydrocarbons, PAHs, carbon-based molecules linked to life's origin. These compounds, stable in the nebula's harsh radiation, may settle in protoplanetary disks where planets form. The Murchison meteorite, which fell to Earth in 1969, contained amino acids, suggesting that such molecules delivered by stellar dust could seed life on young planets. The dynamics of element formation reveal a universe in constant transformation. Supernovae, occurring roughly once every 50 years in a galaxy like ours, inject energy and material into the interstellar medium, triggering waves of star formation. Their shock waves compress gas clouds, initiating gravitational collapse. Planetary nebulae, though less violent, are more common, with thousands dotting the Milky Way. Their gentler ejections, lasting thousands of years, preserve delicate molecules that supernovae might destroy. The Butterfly Nebula's dust, for instance, contains crystalline silicates found in comets and planetary disks, linking it directly to planet formation. This cosmic furnace challenges our understanding of creation. On Earth, death signals an end, but in the cosmos, it is a catalyst. The Butterfly Nebula's glowing lobes, sculpted by stellar winds, are not mere remnants, but engines of renewal. Their elements, merging with the interstellar medium, contribute to new stars and planets. Supernovae, with their explosive power, play a similar role, scattering the heavy elements needed for complex chemistry. Together, they build the universe's complexity, from the simple hydrogen of the Big Bang 13.8 billion years ago to the intricate galaxies we see today. Philosophically, this cycle resonates deeply. The elements in our bodies, carbon, oxygen, iron, were forged in stellar deaths connecting us to the cosmos. The Butterfly Nebula, with its radiant symmetry, embodies this paradox. A star's end fuels new beginnings. Its dust drifting across light years may seed planets with the potential for life. Supernovae, with their violent brilliance, contribute the heavier elements that make such planets possible. This interplay of destruction and creation invites us to ponder our place in the universe, not as isolated beings, but as part of a grand, interconnected story. The scientific study of these processes deepens the mystery. How do complex molecules survive the harsh conditions of stellar death? In the Butterfly Nebula, dust grains act as shields, protecting organic compounds from radiation. In supernovae, rapid reactions in the explosion's aftermath create stable, heavy elements. Observations with telescopes like ALMA reveal these processes in action, showing molecular clouds enriched by stellar remnants. Yet gaps remain. How do these molecules transition from cosmic dust to living systems? The presence of amino acids in meteorites hints at a universal chemistry, but the leap to life remains elusive. The broader galactic context amplifies this narrative. Galaxies like Andromeda, 2.5 million light-years away, evolve through the same cycle of stellar birth and death. Supernovae and planetary nebulae shape their chemical landscapes, driving the formation of new stars and planets. The Milky Way's spiral arms, glowing with star-forming regions, owe their vibrancy to this process. The Butterfly Nebula, though a fleeting moment, contributes to this cosmic evolution, its dust a legacy that may spark worlds unknown. As we reflect on this cosmic furnace, we confront a profound question. If stellar deaths produce the elements of life, could they also seed life across the universe? The Butterfly Nebula's gentle winds and the violent blasts of supernovae together create a universe rich with possibility. Their elements, woven into new stars and planets, suggest that life may not be unique to Earth. This possibility pulls us toward a deeper inquiry. Could the cosmic cycle of destruction and creation hold the key to discovering life beyond our world, reshaping our understanding of the universe's potential? How does the universe weave new worlds from the ashes of stars? The Butterfly Nebula, its glowing wings, a testament to a star's demise, scatters dust and gas that ripple through the cosmos, shaping galaxies, stars, and planets over eons. These remnants, forged in stellar hearts, coalesce into structures of breathtaking complexity, from the spiral arms of the Milky Way to the rocky crust of Earth. This cosmic evolution, spanning billions of years, transforms chaos into order, raising a profound question. Could the dust of dying stars like those in NGC 6302 spark planets teeming with life? The dance of galactic matter reveals a universe where destruction fuels creation, crafting worlds from the embers of ancient suns. The interstellar medium, a vast sea of gas and dust, serves as the universe's crucible, comprising mostly hydrogen and helium. From the Big Bang 13.8 billion years ago, it is enriched by stellar deaths. Planetary nebulae, like the Butterfly Nebula 3800 light-years away, release lighter elements, carbon, oxygen, nitrogen, through stellar winds. Supernovae, the explosive ends of massive stars, scatter heavier elements like iron and gold. The Crab Nebula, a supernova remnant 6,500 light-years distant, exemplifies this, its shock waves dispersing elements across space. These contributions, gentle and violent, enrich the interstellar medium, providing the raw materials for new celestial bodies. This enriched medium fuels star formation in molecular clouds, dense regions where gravity reigns. The Orion Nebula, 1,344 light-years away, is a stellar nursery where gas and dust collapse into dense knots. As these knots contract, Temperatures soar to millions of Kelvin, igniting fusion and birthing stars, dust grains, some from nebulae, like NGC 6302, play a critical role, cooling the cloud to aid collapse. These grains, rich in silicates and carbon compounds, absorb starlight, radiating heat and allowing the cloud to contract further. Over millions of years, this process spawns stars of varying masses, from faint red dwarfs to blazing giants, each contributing to the galaxy's evolution. The formation of planets follows a similar path. Around young stars, residual gas and dust form protoplanetary disks, swirling rings where creation unfolds. In these disks, dust grains collide, sticking together to form pebbles, then boulders, and eventually planetesimals. The Butterfly Nebula's dust, laden with carbon-based molecules like polycyclic aromatic hydrocarbons, PAHs, could join such disks, delivering the elements needed for rocky planets. Our solar system, born 4.6 billion years ago, emerged from such a disk, its planets coalescing from dust enriched by ancient stellar deaths. Earth's crust, rich in silicon and oxygen, traces its origins to nebulae like NGC 6302. This process, though slow and seemingly chaotic, is elegantly inevitable. Gravity, the universe's architect, orchestrates the coalescence of matter. In molecular clouds, turbulence and magnetic fields shape gas into filaments, where stars form. In protoplanetary disks, gravitational instabilities drive the growth of planets. Observations of young stars like those in the Taurus molecular cloud 450 light-years away reveal disks teeming with dust grains growing over millions of years. ALMA telescope images show gaps in these disks, carved by forming planets, confirming this gradual yet relentless process. The universe, through countless cycles of stellar birth and death, builds complexity from simplicity. Galaxies themselves evolve through this cycle. The Milky Way, 100,000 light-years across, owes its spiral structure to waves of star formation triggered by supernovae and stellar winds. Each stellar death enriches the interstellar medium, fueling new stars and planets. Over billions of years, galaxies merge as the Milky Way will with Andromeda in 4.5 billion years, blending their dust and gas to spark new creation. The Butterfly Nebula's contributions, though small, are part of this grand narrative. Its dust, scattering into the interstellar medium, may join molecular clouds, triggering star formation in distant regions of the galaxy. The chemical richness of this process is profound. The Butterfly Nebula's dust contains organic molecules detected through infrared spectroscopy that resemble life's building blocks. PAHs found in its glowing lobes are also present in meteorites like Murchison, which carried amino acids to Earth. These molecules, surviving the harsh radiation of a white dwarf at 250,000 Kelvin, suggest a universal chemistry. In protoplanetary disks, such compounds could seed planets with the ingredients for life. Exoplanet surveys, like those of the TRAPPIST-1 system, reveal rocky worlds in habitable zones, hinting that such chemistry may be common across the cosmos. This cycle contrasts chaos with inevitability. Star formation appears random, driven by turbulent clouds and chance collisions, yet it follows a predictable path. Gravity ensures that dust and gas coalesce, forming stars and planets with remarkable consistency. The Butterfly Nebula's delicate wings, sculpted by stellar winds at 600,000 miles per hour, belie the ordered physics at play. Its dust, merging with molecular clouds, contributes to this inevitability, ensuring that each stellar death paves the way for new worlds. This elegance, observed across galaxies like NGC 4414, 62 million light-years away, reveals a universe governed by both chance and destiny. Philosophically, this evolution captivates our imagination. The elements in our bodies, carbon, oxygen, iron, were forged in stellar deaths, linking us to the cosmos. The Butterfly Nebula's dust, drifting across light-years, may one day form planets orbiting alien suns, perhaps hosting life. This connection transforms our view of the universe from a cold, distant void to a vibrant crucible of possibility. Each cycle of birth and death, from the Big Bang to today, builds complexity, suggesting that life may not be an accident but an outcome of cosmic evolution. The scientific mystery deepens this narrative. How do dust grains survive the violent conditions of stellar death? In the Butterfly Nebula, protective coatings of ice or carbon shield molecules from radiation. In protoplanetary disks, how do these grains grow into planets? Computer models suggest collisions and electrostatic forces drive this process, but gaps remain. Observations of disks around stars like HL Tauri, 450 light-years away, show intricate structures hinting at unseen planets. These puzzles fuel our curiosity, pushing us to explore the mechanisms that transform dust into worlds. The broader galactic context underscores this cycle's significance. Galaxies evolve through stellar deaths, each supernova and planetary nebula adding to their chemical wealth. The Milky Way's 100 billion stars, formed over billions of years, reflect this process. The Butterfly Nebula, though a fleeting moment, contributes to this legacy, its dust a seed for future creation. Across the universe, in galaxies like Messier 87, 55 million light-years away, similar cycles unfold, suggesting a cosmos alive with potential. As we ponder this evolution, a profound question emerges. If stellar dust can form planets, could it also nurture life? The Butterfly Nebula's organic molecules, scattered into the cosmos, hint at a universe where life may be common. This possibility pulls us toward a deeper inquiry. Are we alone, or is the cosmos teeming with worlds born from the same dust that shaped our own, ready to reveal the secrets of life's universal potential? Could the faint glow of a distant nebula hold the blueprint for life? The Butterfly Nebula, its radiant wings shimmering 3,800 light-years away, scatters dust rich with organic molecules, whispering possibilities of creation across the cosmos. In the vast emptiness between stars, where silence reigns, scientists seek a signature of life clues that the same stellar ashes that birthed Earth might spark existence elsewhere. This quest, blending cutting-edge missions with speculative wonder, contrasts the desolate void of space with the vibrant potential of stellar dust. If a star's death marks not an end but a beginning, could nebulae like NGC 6302 reveal a universal recipe for life? The interstellar medium, a sparse tapestry of gas and dust, is a treasure trove of chemical complexity. Planetary nebulae like the Butterfly Nebula release carbon, oxygen, and nitrogen forged in a star's core. Its dust grains, some smaller than a micron, carry polycyclic aromatic hydrocarbons, PAHs, carbon-based molecules linked to life's origins. Infrared observations by the Spitzer Space Telescope reveal these compounds in NGC 6302, glowing amid the nebula's lobes, sculpted by stellar winds at 600,000 miles per hour. These molecules, stable in the harsh radiation of a white dwarf burning at 250,000 Kelvin, suggest that the chemistry of life is not unique to Earth but woven into the cosmos. Scientists probe this chemistry through missions targeting the interstellar medium and beyond. The Atacama Large Millimeter to Submillimeter Array, ALMA, peering into molecular clouds like the Taurus Molecular Cloud, 450 light-years away, detects complex molecules methanol, formaldehyde, even glycine, an amino acid. These clouds, enriched by nebulae like NGC 6302, are stellar nurseries where dust and gas coalesce. The presence of organic molecules in such regions hints that the building blocks of life form naturally in space. The Rosetta mission, which studied Comet 67P in 2014, found amino acids and organic compounds, likely delivered from nebulae, suggesting that comets act as cosmic couriers, carrying life's ingredients to planets. Exoplanet research amplifies this search. The Kepler and TESS missions have identified thousands of exoplanets, many in habitable zones where liquid water might exist. The TRAPPIST-1 system, 39 light-years away, hosts 7 rocky planets, 3 potentially habitable. These worlds, formed from dust enriched by stellar deaths, could harbor the same organic molecules found in the Butterfly Nebula. The James Webb Space Telescope, launched in 2021, studies the atmospheres of such exoplanets, searching for biosignatures, gases like oxygen or methane that might indicate life. If these planets formed from dust similar to NGC 6302's, their atmospheres could reveal a cosmic connection to life's origins. Asteroids and meteorites offer further clues. The Murchison meteorite, which fell in 1969, contained over 70 amino acids, suggesting that organic molecules from stellar dust survived journeys to planetary surfaces. Japan's Hayabusa 2 mission, returning samples from asteroid Ryugu in 2020, found organic compounds and water-bearing minerals, likely tracing back to nebulae. These findings imply that the interstellar medium, enriched by stellar deaths, delivers life's building blocks to forming planets. The Butterfly Nebula's dust, with its PAHs and silicates, could play a similar role, scattering seeds of life across the galaxy. The contrast between space's vast emptiness and its creative potential is striking. The interstellar medium, with a density a trillion times lower than Earth's atmosphere, seems an unlikely cradle for life. Yet, within molecular clouds, shielded from radiation, dust grains catalyze chemical reactions. Atoms collide on grain surfaces, forming molecules, like water and ethanol. In the Butterfly Nebula, intense radiation drives similar chemistry, producing complex organics that survive in protective dust coating. Laboratory experiments simulating interstellar conditions show that ultraviolet light and cosmic rays transform simple atoms into amino acids, suggesting that life's chemistry is a universal process unfolding wherever stars die. This search extends beyond our galaxy. Observations of galaxies like Messier 82, 12 million light-years away, reveal organic molecules in their interstellar medium, hinting that the chemistry of life is cosmic in scope. The Butterfly Nebula, though a single moment in the Milky Way's 100 billion star saga, contributes to this universal narrative. Its dust, merging with molecular clouds, may trigger star formation, perpetuating the cycle. ALMA's detection of complex molecules in distant galaxies suggests that nebulae like NGC 6302 are not anomalies, but part of a cosmic pattern where stellar deaths seed the potential for life. Philosophically, this quest reshapes our view of existence. The Butterfly Nebula's glowing lobes, born from a star's collapse, symbolize a universe where death fuels creation. The carbon in our DNA, the oxygen in our lungs, these elements, forged in ancient stars, connect us to nebulae across the cosmos. This linkage sparks awe. Are we the only beings pondering this mystery? Or do other worlds, born from similar dust, harbor life? The nebula's fleeting beauty, lasting mere thousands of years, underscores the impermanence of existence. Yet its legacy endures in the molecules it scatters. Scientifically, the search for life's signature is fraught with challenges. How do complex molecules transition to living systems? On Earth, life emerged in warm, wet environments, but in space, conditions are harsh. The Butterfly Nebula's organic compounds, protected by dust, suggest resilience, but the leap to life remains elusive. Missions like Europa Clipper, set to explore Jupiter's moon in the 2030s, seek subsurface oceans where stellar-derived molecules might foster life. Similarly, the Dragonfly mission to Titan, planned for 2034, will study a moon rich in organic, potentially delivered by comets bearing nebular dust. These missions bridge the gap between cosmic chemistry and biology. The galactic context amplifies this narrative. The Milky Way evolves through stellar deaths, each nebula and supernova enriching its chemical landscape. Over 13.8 billion years, this process has built complexity from primordial hydrogen to the intricate galaxies we see today. The Butterfly Nebula's dust, joining molecular clouds, contributes to this evolution, potentially sparking planets in distant systems. Observations of star-forming regions, like the Carina Nebula, 7,500 light-years away, show this cycle in action, with dust and gas coalescing into new stars and planets. This search for life's signature raises a profound question. Is stellar dust the beginning of something greater? The Butterfly Nebula, with its organic rich dust, suggests that life's building blocks are scattered across the cosmos. If these molecules can form on Earth, why not on exoplanets orbiting distant stars? The possibility that nebulae like NGC 6302 seed life transforms our view of the universe from a cold void to a fertile crucible. This idea pulls us toward a deeper inquiry. Could the dust of dying stars drifting through the cosmos reveal a universal signature of creation, hinting at life's presence beyond our world? What does a star's death reveal about the nature of existence? The Butterfly Nebula, its luminous wings unfurling 3,800 light-years away, stands as a radiant emblem of cosmic renewal. Born from a star's collapse, its glowing dust and gas weave a narrative of destruction transforming into creation. This celestial cycle, where endings birth beginnings, challenges our view of death as final. Could the ashes of a star scattered across the void hold the key to life's deeper meaning? By blending the tangible splendor of NGC 6302 with existential questions, we explore a universe where death is not an end, but a vital step in an eternal dance of rebirth. The Butterfly Nebula, with its vibrant lobes stretching over 2 light-years, embodies this paradox. Its progenitor star, once several times our Sun's mass, shed its outer layers in winds reaching 600,000 miles per hour, leaving a white dwarf burning at 250,000 Kelvin. This radiant core illuminates the nebula's gases helium, oxygen, nitrogen, creating a celestial tapestry. Yet this beauty arises from destruction. The star's collapse, a moment of cosmic violence, releases carbon and silicates, elements that drift into the interstellar medium to form new stars and planets. This cycle, observed across galaxies, mirrors a profound truth. What we perceive as death fuels creation. On Earth, death often signals finality, a severing of existence. But in the cosmos, it is generative. The Butterfly Nebula's dust, rich with organic molecules like polycyclic aromatic hydrocarbons, may seed planets with life's building blocks. The carbon in our cells, the oxygen in our breath, these were forged in ancient stars, their deaths knitting us into the universe's fabric. This connection transcends science, inviting reflection on our place in a cosmos where every end sparks a beginning. The nebula's fleeting glow, lasting mere thousands of years, underscores life's impermanence, yet its legacy endures in the worlds it may create. This cycle challenges our existential assumptions. If a star's death fosters new systems, what does this mean for life's purpose? The Butterfly Nebula, with its delicate symmetry, suggests a universe pulsing with intention. Its dust, scattering across light-years, carries the potential for life, perhaps on planets orbiting alien suns. This possibility reframes destruction as a creative act, a necessary unraveling to weave new tapestries. Philosophers like Heraclitus, who saw change as the essence of existence, echo this cosmic rhythm. The nebula's transformation from star to glowing remnant to cosmic seed mirrors a universe in constant flux, where death and rebirth are intertwined. The contrast between destruction and creation resonates deeply. In human experience, loss often feels absolute, yet the cosmos reveals a different story. Supernovae, exploding with the force of 1 billion suns, scatter iron and gold, elements essential for planets like Earth. Planetary nebulae like NGC 6302 gently release carbon and oxygen, fostering organic chemistry. Together they enrich the Milky Way, a galaxy of 100 billion stars shaped by 13.8 billion years of stellar cycles. This interplay suggests that destruction is not an end, but a catalyst, a clearing of the old to make way for the new. The nebula's radiant wings, born from chaos, embody this generative power. This perspective invites us to reconsider life's fragility. The Butterfly Nebula's ephemeral beauty, fading within 20,000 years, mirrors our own transient existence. Yet its dust, merging with molecular clouds like those in Orion, 1,344 light-years away, ensures continuity. This cycle connects us to the cosmos, suggesting that our lives, though brief, are part of an eternal narrative. The elements in our bodies, forged in stellar crucibles, tie us to stars long gone. This kinship sparks awe. We are not separate from the universe, but woven into its story, our existence a thread in its vast tapestry. The philosophical implications extend to the search for meaning. If stellar death seed life is the universe, inherently creative, the Butterfly Nebula's organic molecules detected by infrared telescopes hint at a cosmos teeming with potential. These compounds, surviving harsh radiation, may settle on distant planets, fostering chemistry akin to Earth's primordial soups. The TRAPPIST-1 system, 39 light-years away, with its rocky planets, could harbor such seeds, delivered by comets bearing nebular dust. This possibility suggests that life may not be an anomaly, but a natural outcome of cosmic evolution, raising questions about our uniqueness in the universe. Yet this cycle also evokes mystery. Why does the universe recycle its matter so elegantly? The Butterfly Nebula's symmetry, possibly shaped by a binary star or magnetic fields, suggests an order beneath the chaos. This order, seen in the spiral arms of galaxies like Andromeda, 2.5 million light-years away, hints at a deeper purpose. Is the universe a random cascade of events, or does it pulse with intention? The nebula's dust, carrying life's building blocks, invite speculation. Could the cosmos be designed to foster life, each stellar death a deliberate step toward creation? This question bridges science and philosophy. Observations of nebulae like NGC 6302 reveal complex chemistry. PAHs, silicates, water vapor, suggesting that life's ingredients are universal. Missions like the James Webb Space Telescope, studying exoplanet atmospheres, seek biosignatures that could confirm this. Yet the leap from molecules to life remains elusive. On Earth, life emerged in warm, wet conditions, but in space, harsh radiation challenges such chemistry. The resilience of the Butterfly Nebula's dust, shielding organic compounds, suggests that life's potential may be woven into the cosmos, waiting for the right conditions to flourish. This cosmic cycle also mirrors human narratives of renewal. Myths across cultures, phoenixes rising, cycles of creation echo the universe's rhythm. The Butterfly Nebula, transforming from a dying star to a seedbed of possibility, embodies this archetype. Its wings, glowing against the void, symbolize hope. Even in destruction, there is promise. This resonates with our audience who seek meaning in a universe both vast and intimate. The nebula's story, connecting our atoms to ancient stars, offers a sense of belonging, a reminder that we are part of something greater. The galactic context amplifies this reflection. The Milky Way evolves through stellar deaths, each nebula and supernova enriching its chemical landscape. Over billions of years, this process has built complexity, from primordial hydrogen to intricate galaxies. The Butterfly Nebula, though, a fleeting moment, contributes to this evolution, its dust sparking new stars in regions like the Carina Nebula, 7,500 light-years away. This relentless cycle suggests a universe driven by renewal, where every death paves the way for new worlds, perhaps alive with beings pondering the same questions we do. As we gaze at the Butterfly Nebula, we confront a profound truth. Death is not an end, but a transformation. Its dust, drifting through the cosmos, may birth planets teeming with life. This possibility challenges us to see destruction as a creative force, a necessary step in the universe's eternal renewal. The nebula's radiant wings, a fleeting monument to a star's sacrifice, pull us toward a deeper question. If death fuels life across the cosmos, what does this mean for our own existence? And could it hint at a universal purpose waiting to be discovered? Can humanity wield the cosmic forge that shapes stars? The Butterfly Nebula, its glowing wings sprawling 3,800 light-years away, scatters dust and gas remnants of a star's death that have seeded planets and life across eons. These stellar ashes, rich with carbon, oxygen, and organic molecules, hint at untapped potential. Could we one day harness these materials to craft technologies, colonize distant worlds, or even spark synthetic life? This vision, blending scientific ambition with speculative wonder, contrasts the raw power of stellar processes with humanity's audacious dreams. The death of stars, far from a cosmic tragedy, could become a wellspring of ingenuity, transforming our future in the universe. The Butterfly Nebula NGC 6302 exemplifies the universe's creative legacy. Its progenitor star, once several times our Sun's mass, shed its outer layers in winds reaching 600,000 miles per hour, forming luminous lobes spanning 2 light-years. The white dwarf at its core, blazing at 250,000 Kelvin, ionizes gases helium, nitrogen, oxygen, while dust grains carry silicates and polycyclic aromatic hydrocarbons, PAHs. These molecules, detected by infrared telescopes like Spitzer, are precursors to life found in meteorites and comets. This chemical richness, born from a star's demise, fuels the interstellar medium where new stars and planets form. Could humanity tap this cosmic reservoir to reshape our destiny? The scientific potential of stellar materials is staggering. Dust from planetary nebulae like NGC 6302 contains carbon-based compounds and silicates essential for advanced technologies. Carbon, versatile and abundant, forms the basis of nanotechnology. Graphene, carbon nanotubes, and diamond-like structures with unparalleled strength. Silicates, found in Earth's crust, are key to ceramics and semiconductors. Harvesting such materials from space could revolutionize manufacturing. Asteroid mining, already pursued by missions like NASA's OSIRIS-REx, which returned samples from Bennu in 2023, shows the feasibility of extracting resources from celestial bodies. Dust from nebulae, though diffuse, could be collected in molecular clouds where it concentrates, offering a future source for space-based industries. Colonizing new worlds demands resources that stellar dust could provide. Exoplanets in systems like TRAPPIST-1, 39 light-years away, likely formed from dust enriched by nebulae. Terraforming these worlds, making them habitable, requires water, oxygen, and organic compounds, all present in nebula dust. The Butterfly Nebula's grains, carrying water vapor and PAHs, could be processed to create breathable atmospheres or fertile soils. Future technologies like robotic harvesters or plasma-based collectors might gather these materials from interstellar clouds. The European Space Agency's studies on in-situ resource utilization for Mars using local regolith suggest that similar techniques could exploit nebula dust, enabling sustainable colonies on distant planets. The speculative leap to synthetic life pushes this vision further. The Butterfly Nebula's organic molecules resembling Earth's amino acids hint at a universal chemistry. On our planet, life emerged from such compounds in primordial ocean. Could we replicate this in laboratories or on alien worlds? Synthetic biology, already creating artificial cells on Earth, could use nebula dust to engineer life forms tailored for extraterrestrial environments. For example, microbes designed to thrive on Mars could be seeded with carbon and nitrogen from nebula dust, kickstarting ecosystems. The 2024 DARPA program on synthetic organisms for extreme conditions shows this is no longer pure fantasy, but an emerging frontier. This potential contrasts with the challenges of harnessing stellar materials. The interstellar medium is vast and sparse, with densities 1 trillion times lower than Earth's atmosphere. Collecting dust from nebulae like NGC 6302 scattered across light-years requires technologies far beyond current capabilities. Advanced propulsion, like ion drives tested in NASA's X-3 thruster, could reach molecular clouds, but gathering diffuse particles demands innovative solutions, perhaps magnetic traps or nanotechnology-based collectors. Energy costs are daunting. Processing stellar dust into usable materials requires immense power, possibly from fusion reactors mimicking the stars themselves. These hurdles, though formidable, fuel scientific imagination, pushing the boundaries of what's possible. The philosophical implications of this vision are profound. Stellar deaths, like the Butterfly Nebulas, are not tragedies, but opportunities. Their dust, seeding the cosmos with life's ingredients, suggests a universe inherently creative. If we harness these materials, we become co-creators, shaping worlds as stars do. This mirrors ancient myths of renewal phoenixes rising from ashes, recast in a cosmic context. The nebula's fleeting glow, lasting only 20,000 years, reminds us of our own impermanence, yet its legacy inspires hope. By tapping stellar resources, we could extend our presence across the galaxy, weaving humanity into the universe's eternal cycle. This ambition raises ethical questions. Should we manipulate the cosmos for our gain? Harvesting nebula dust could disrupt star-forming regions, altering galactic evolution. Creating synthetic life risks unforeseen consequences, as seen in debates over genetic engineering. The 2025 UNESCO guidelines on space resource ethics urge caution, emphasizing sustainability. Yet the potential to colonize new worlds, or spark, life aligns with humanity's drive to explore and create, echoing the universe's own rhythm of destruction and rebirth. Balancing ambition with responsibility will define our cosmic future. Scientific missions pave the way for this vision. The James Webb Space Telescope, studying exoplanet atmospheres, identifies worlds that might support life seeded by nebula dust. The 2034 Dragonfly mission to Titan, rich in organic, will explore how stellar-derived molecules foster prebiotic chemistry. Asteroid missions like Japan's Hayabusa 2 demonstrate resource extraction, a stepping stone to harvesting interstellar dust. Future projects like the proposed interstellar probe aim to explore the interstellar medium directly, potentially mapping regions rich in nebula materials. These efforts, though nascent, bring us closer to wielding the power of stars. The galactic context amplifies this potential. The Milky Way, shaped by 13.8 billion years of stellar cycles, relies on nebulae and supernovae to enrich its 100 billion stars. The Butterfly Nebula's dust, merging with clouds like those in the Carina Nebula, 7,500 light-years away, fuels new star formation. Harnessing this process could transform humanity into a galactic species, building habitats in star-forming regions or on exoplanets. Galaxies like Andromeda, 2.5 million light-years away, show similar cycles, suggesting that stellar resources are a universal opportunity waiting for a species bold enough to claim them. This vision challenges our view of stellar death. The Butterfly Nebula, its wings a testament to a star's sacrifice, is not a monument to loss, but a beacon of possibility. Its dust, carrying life's building blocks, could fuel technologies, colonies, or new forms of life. This reframes destruction as a creative force, inviting us to see stars not as fleeting but as eternal engines of creation. The nebula's story, connecting our atoms to the cosmos, inspires a future where we harness its power, becoming stewards of a universe alive with potential. As we contemplate this future, a profound question emerges. If we can harness the materials of dying stars, what limits remain? The Butterfly Nebula's dust, drifting through the cosmos, holds the promise of new worlds and lives. This potential pulls us toward a grander inquiry. Could our mastery of stellar creation redefine humanity's role in the universe, transforming us from observers to architects of cosmic renewal? What is the true legacy of a star's final breath? The Butterfly Nebula, its radiant wings glowing 3,800 light-years away, stands as a testament to a profound cosmic truth. Death is not an end, but a catalyst for creation. Its dust, scattered by a dying star, carries the seeds of new stars, planets, and perhaps life itself. This endless cycle of creation and destruction weaves through the universe, binding galaxies, stars, and even our own existence into a tapestry of eternal renewal. As we gaze upon the cosmos, we are invited to embrace both its endings and beginnings, finding wonder in a universe that transforms loss into possibility. The Butterfly Nebula NGC 6302 encapsulates this cycle. Its progenitor star, once several times our sun's mass, shed its outer layers in winds blazing at 600,000 miles per hour, forming luminous lobes that span 2 light-years. The white dwarf at its core, burning at 250,000 Kelvin, ignites the surrounding gas helium, oxygen, nitrogen into a vibrant display. Yet this spectacle of destruction releases carbon-rich dust and organic molecules like polycyclic aromatic hydrocarbons into the interstellar medium. These particles, detected by telescopes like Spitzer, are not mere debris but the raw materials for new celestial bodies, linking a star's death to the birth of worlds. This cycle reverberates across the cosmos. In molecular clouds like the Orion Nebula 1344 light-years away, dust and gas coalesce under gravity's pull, igniting new stars. These stars, in turn, forge elements in their cores, only to release them in their final moments through gentle winds in planetary nebulae or explosive supernovae. The Crab Nebula, 6,500 light-years distant, marks a supernova's violent end, scattering iron and gold across space. These elements, forged in stellar hearts, enrich the Milky Way, a galaxy of 100 billion stars shaped by 13.8 billion years of such cycles. Each death fuels creation, building complexity from the universe's primordial simplicity. The philosophical weight of this cycle is profound. On Earth, we often view death as a final curtain, a severance of existence. Yet the cosmos reveals a different truth. Destruction is generative. The Butterfly Nebula's dust, drifting through the void, may settle in protoplanetary disks forming planets like ours. The carbon in our bodies, the oxygen we breathe, these were born in ancient stars, their deaths weaving us into the cosmic narrative. This connection transforms our perspective, casting us not as isolated beings, but as integral parts of an eternal dance where every end sparks a new beginning. This dance extends to galaxies themselves. The Milky Way's spiral arms, glowing with star-forming regions, owe their vibrancy to stellar deaths. Supernovae and nebulae like NGC 6302 enrich the interstellar medium, triggering waves of star formation. Galaxies merge, as ours will, with Andromeda in 4.5 billion years, blending their materials to forge new systems. This relentless evolution, observed in distant galaxies like Messier 87, 55 million light-years away, reveals a universe in constant transformation, where destruction and creation are two sides of the same coin. The possibility of life amplifies this wonder. The Butterfly Nebula's organic molecules, resilient in the face of intense radiation, hint at a universe primed for biology. These compounds, found in meteorites like Murchison, suggest that life's building blocks are scattered across the cosmos. Exoplanets in systems like TRAPPIST-1, 39 light-years away, may harbor similar materials delivered by comets bearing nebular dust. Missions like the James Webb Space Telescope search for biosignatures on such worlds, probing whether life is a cosmic rarity or a universal outcome. The nebula's dust, carrying the seeds of possibility, invites us to imagine a universe teeming with life. This cycle challenges us to reframe destruction. The Butterfly Nebula's fleeting beauty, fading within 20,000 years, mirrors life's impermanence, yet its legacy endures. Its dust, merging with clouds like those in the Carina Nebula, 7,500 light-years away, sparks new creation. This resilience echoes in human stories of renewal, myths of phoenixes, cycles of rebirth that find their cosmic parallel in the stars. The nebula's radiant wings, born from a star's collapse, symbolize hope. Even in loss, there is promise. This resonates deeply, offering a sense of connection to a universe that transforms endings into beginnings. Scientifically, this cycle raises tantalizing questions. How do organic molecules survive the harsh conditions of stellar death? In the Butterfly Nebula, dust grains shield complex compounds, allowing them to drift into molecular clouds. How do these materials coalesce into planets and life? Observations of protoplanetary disks like those around HL Tauri, 450 light-years away, show dust growing into planetesimals, but the leap to biology remains elusive. These mysteries fuel our curiosity, driving missions like Europa Clipper and Dragonfly to explore environments where stellar-derived molecules might spark life. Philosophically, the cycle invites reflection on existence itself. If a star's death seeds new worlds, is the universe inherently creative? The Butterfly Nebula's symmetry, possibly sculpted by a binary star, suggests an underlying order. This order, seen in the intricate structures of galaxies, hints at a cosmos pulsing with purpose. Are we, as products of stellar dust, part of a deliberate design or the result of cosmic chance? The nebula's legacy, connecting our atoms to ancient stars, suggests that our existence is intertwined with the universe's story, a narrative of constant renewal. As we contemplate this cosmic dance, we see the universe anew. Picture a vast, shimmering expanse, stars igniting, fading, and igniting again, their dust weaving galaxies, planets, and life. The Butterfly Nebula, a fleeting moment in this saga, embodies its essence: destruction, births, creation. Its glowing lobes, a monument to a star's sacrifice, remind us that endings are beginnings. This perspective fills us with wonder, urging us to see beauty in both the fall and rise of cosmic cycles, each a step in an eternal journey of renewal. This vision leaves us with a final reflection. If the dust of dying stars can spark life, what possibilities await? The Butterfly Nebula's radiant legacy points to a universe alive with potential, where every death fuels a new dawn. As we ponder our place in this cosmic ballet, we are left with a profound sense of awe. The cycle of creation and destruction, forever turning, binds us to the stars, inviting us to dream of worlds yet to be born.